Hello, welcome to chapter 7, part 1, properties of expectations. Okay, so we're going to start with talking about how to figure out the expectation of sums of random variable. So to recap, if you remember what we did before, if we're only working with one random variable, okay, so if I have like a random variable x, right, and now if I have a function gx, okay, then what we know that if you're working with a discrete case, you are doing a summation, right, of all of the possible x values of gx times fx, where fx, or sometimes you write px, is the PMF, okay, for the discrete case, okay? And then for the continuous case, we know that the expectation of this function gx becomes the integral, right, of gx fx dx, where fx is the PDF, sorry, so let me write down here, okay? So depending on what type of variables you're working with, you have this two different set of approaches, okay? So now, suppose you have a function, okay, now it's a gxy function, okay? It is a real value function of random variables x and y at the same time, okay? So for example, something like x plus y, x minus y, x times y, things like that, they are, right? Or x squared plus y, any kind of function you can think of about x and y at the same time, it could be a gx function, okay? So for the discrete case, meaning that if I have both of them, both x and y to be discrete, okay, then the expectation of this gxy function, as you can see, becomes a double sum, okay, because we're summing over all of x and all of y, okay? We have the gxy function, which is the function we're evaluating, multiplies with the joint, okay, so here, this is the joint PMF, okay? And similarly, for the continuous case, we're doing a double integral, okay? Now here is gxy, is the function that we're evaluating. This is the joint PDF, okay? And then double integral, you do in dx, dy, or maybe whichever is easier, you do dy, dx, okay? So try to figure out the way that works the best for the scenario, okay? So now let's look at example and a very important result, okay? So let x and y be random variables with the joint PDF, okay? So here, as you can see, we are working with continuous, okay? And so as you will see soon, we will be doing a double integral in this case, okay? So the joint PDF is fxy, okay? They ask you to find the expectation of the sum of the two, okay? So following what we had from the previous slide, okay? So the so let me write it out over here, okay? So the gxy function that we're dealing with over here is the x plus y, okay? So notice that, remember earlier, the formula that we know is the expectation of gxy function, okay? So here we're looking for expectation of x plus y, so that's another, just think about it, right? That this is a gxy function, all right? So let's get started with that, okay? So remember what we're having is the joint PDF, right? Multiplies with the gxy function that we're dealing with, and then right now I'm just writing dx, dy, generically in a sense, and all of the bounds are from -infinity to +infinity, okay? So one thing we can keep working on this, as you can see that, well, it's x plus y, right? Multiplies with the fxy. So I can actually break this into two parts, okay? The first part will be, I'm looking at the part of x times fxy, okay? So I'm doing it over here. Notice that I start to write dy dx. You're gonna see soon why I do the change, because it will be easier to do the integration soon, as you can see it, okay? And then the second part will be the y part, right? The y times fxy part, and then I'm just doing dx dy because it will be easier to do next as well, okay? So from this line to this line is purely just break x plus y times fxy into two parts, and then there are two separate integrals here. Okay, so now I hope you can see why I want to do like dy dx in the first place. In the first case, because if I'm doing dy dx, one thing we could immediately do is that this x, okay, multiply with fx, y. This x is a constant, right, with respect to y. So I can bring my x outside of the first integral or the inner integral, okay? So now I have x here, and then I'm doing my integration, right, of fxy dy from -infinity to +infinity. Okay, similarly, I do that. for my second term. And then that's also why I'm doing dx dy over here, because y is a constant with respect to x, so I can bring it out. Okay, so now to move forward, notice what this is. Okay, so let's take a pause. This is doing a joint, right? Integration of the joint of x and y, joint PDF with respect to y. And we know that when we do that integration, this will give you, right, the marginal of x. Okay, you're integrating out. So let me write it this way. Okay, you're integrating out y of the joint, so you're getting the marginal of x. Okay, so similarly, you're gonna get the marginal of y over here. Okay, so that's what we're gonna do for the next step. Okay, let me try to erase maybe this part. Okay, but you know what I mean, right? So here we are getting the integral. The inner integral becomes a marginal density, marginal PDF of x. Okay, this is the marginal density of y over here. Okay, and then lastly, if we look at this term, this is our old friend. Okay, we're doing integral of x times fx. Okay, dx. Okay, so what that is, that's the expectation of x. Okay, similarly, we get here the second term is the expectation of y. So this goes down to expectation of x plus expectation of y. Okay, so what this is telling us, okay, this example is actually a very important result. Okay, and this is also the title of the section, expectation of sums of random variables. And what this is saying is that if I know the joint PDF, okay, of x and y, the expectation of x plus y is the sum of the two expectations. Okay, so in this slide, we show how you can arrive there. Okay, and then some of the techniques I think are really important to grasp, especially about those integral, double integral integrals. Okay, so this is a general result, like I said. Okay, and then I would just also mention that we showed the case for the continuous, okay, PDF, okay, continuous random variables. But if you also tried to work it out with discrete case, you will work as well. Either one of them is discrete or both of them. And another thing is this result does not require x and y to be independent. Okay, so if you come back to what we showed earlier on this slide of proof, okay, nowhere we assume anything about independence. Okay, and so as you can see, in this case, we don't need them to be independent. You can always apply this result. Okay, moreover, it can be generalized to n random variables. Okay, so here I'm writing x1, x2 through xn. Okay, so the expectation of the sum of them is the sum of all of the expectation of each of them individually. Okay. Okay, so that's a really important general result, and we should be able to use it in many cases. Okay, but I also wanted to bring your attention to another function of xy, which is the product. Okay, so remember, we're working the general result that we have of the joint function over here to find the expectation, right, is the gxy function, and then we have that general result at the beginning to show the expectation of this function. Okay, so earlier, this is the x plus y is the gxy function. Now x times y is the gxy function. Okay, so we have a special case here to show you. Okay, and then we're going to also highlight the implications here. Okay, so the exercise or example here is let x and y be independent. Okay, they're independent random variables. Okay, they have a joint PDF fxy. Okay, you are asked to find the expectation of xy, x times y. Okay, alrighty, so we're going to start one by one. Okay, so remember our gxy function now is x times y, so we put xy over there. Okay, and then it's fxy, which is the joint PDF that we have, and then right now I'm putting down just dx dy. We're going to see whether we're going to do this or maybe switch the order. Okay, so the next step, okay, remember we have a extra condition here. Okay, where also like not only just any kind of x and y, we know that they're independent from each other, and because of that, a very important next step that we can take is to break this joint fxy into the product, right, of the marginal. And that's what we know. If you remember, if two random variables are independent, if they're continuous, then their joint PDF is the product of the two marginals. Okay, it goes the same for the discrete case as well. But since here we're working with continuous random variables, so we're gonna do that one here. Okay, so that gives us to the second step here. So we still keep our xy here. Okay, and our joint fxy becomes fx times fy. okay, and then dx dy, okay? All right, so now if we go to the next step, we're gonna use something very similar to what we did with the x plus y case. That is, if I'm doing the inner integral of dx first, then anything not about x is a constant, right? And meaning that we can bring it outside of the integral. So y is a constant, okay? Fy is another constant, okay? So I can bring both of them outside. That would be a really handy thing to do. So let's see. Okay, so we brought it out, okay? And so they're here. And then the inner one, now you remember, right? We just saw it. This is the expectation of x, okay? So what this does is that, well, we realize that one part of this is, one part of the double integral is the expectation, okay? And once we write it out as an expectation, this ex, okay, becomes a constant, right, with respect to y. So we can further bring that out from the outer integral as well. So meaning that we can bring this outside, okay? So what that does is we have expectation times this single integral, and this single integral, as we know, is the expectation of y, okay? So that's why finally, if x and y are independent, notice that it's very important to have this condition, because if they're not independent, we cannot even go from here to here, okay? This line 1 to line 2 is due to independence, okay? And so what this result is telling us is that if x and y are independent and you have their joint PDF, then the expectation of the product is the product of the expectation, okay? So a couple of notes here. The first one is, like what we were saying earlier, this formula only holds when they're independent, okay? But also this is not a sufficient condition for independence, okay? Meaning that sometimes you might have a expectation of x plus times y indeed becomes, okay, the product of the expectations, but that doesn't say that they're independent, okay? The condition, the sufficient condition for independence, if you remember, is that their joint PDF can be broken down into the product of the marginal PDFs, or like the joint CDF, right, can be broken down into product of the marginal CDF, okay? And those are for the continuous case. If you're working with a discrete case, then it's about the PMF, okay? So what this is saying is that, well, if you know that they're independent, this result holds, okay? But if you have x and y particularly satisfying this result, it does not guarantee that they're independent, okay? But anyway, usually, right, like what this exercise is doing, you're given that they're independent, so you know this result, and then that will be really handy to use, okay? But if you're trying to use this to show some two random variables are independent, then it's not good, okay? The way to show is, if you remember, if you're given the joint of x and y, you need to integrate out one of them, right, to be the marginal of the other one, and then you do that vice versa, and then you check if the product, right, of the marginal PDF is the joint PDF, and that is the way to show independence, not through expectation, okay? But if you do know that they're independent, then you have this handy results that expectation of the product is the product of the expectation. Alrighty, so to recap, okay, we talked about expectation of sum, okay? We started off with only two random variables, but you can generalize it, okay, to any n random variables, okay? And note that here we do not require them to be independent from each other, okay? Working with the sum, they don't need to be independent to use this formula. However, only they're independent, you're able to use the product result, okay? So if x1 through xn, they're independent, then expectation of the product is the product of the expectation, okay? However, we highlight this is not a sufficient condition, okay? Meaning that if you happen to have the expectation of the product equals to the product of the expectation, it does not say that they're independent, okay? Sometimes it could happen that they just happen to be equal to each other, but we also just talked about the sufficient condition is to check if the joint CDF is the product of the marginal CDF, okay, or if the joint PDF is the product of the marginal PDFs, or if you're working with discrete random variables, it is whether the joint PMF is the product of the marginal PMFs.